As it says, my name is Jothy Rosenberg. I'm from Draper, which is a nonprofit independent lab in Kendall Square, Cambridge. It's been there for, it was originally part of MIT, and 40 years ago it spun out and became completely independent. It's about a 1,500 person lab. Does everything from the inertial guidance system for the Trident missiles to making things really small. We've got really microscopic devices. We've got little cameras, little very small celestial navigation that will allow you to navigate when GPS has been denied. And we have a pretty significant cybersecurity group, and we have the network trying to get me to connect to the, and we have this cybersecurity group that I lead right now. And what I wanted to talk to you about was the inherent vulnerability in the processors that we use. And as the previous speaker was pointing out, sometimes we may overblow some of the threats. However, I've been to a number of top secret briefings that talk about exactly who and what is attacking the electric grid. And so it's pretty scary at least what the nation states are doing. And if we just continue with the current approach to dealing with things, they'll be able to have their way. The fact is that the processors that we use in all devices, whether it's your phone or your laptop or a server, are all highly, highly vulnerable. And the reason this has occurred is because the architecture for these processors, which is called the stored memory architecture, was invented by von Neumann in 1945, and has been the same architecture, basically, since then. So during most of that time, especially in the early days, before it was even transistors, they were vacuum tubes, and they were very expensive. And then, you can see in 1970 when Intel's, basically their first microprocessor came out, it had 2,000 transistors. The most recent quad-core has 2.6 billion transistors. So that's Moore's law operating as it has, nice and steady, doubling the number of transistors every 18 months, all that time. But what's changed, of course, is that back in the early days, the concept of somebody attacking your computer was laughable, it was impossible, and now it's not funny at all. So, the Moore's law and the cheap processors led to the internet, led to mobile devices. The iPhone 5S is 1,000 times more powerful than the 1975 Cray 1 supercomputer that cost $1.5 million. So people have a lot of power in their hand, and they're connected to everyone. And now you can reach around the world, and you can try to take advantage of someone. Also, of course, computers increasingly protect valuable things. And another problem is that software has grown to be extremely large and complex. The E-Class Mercedes has 100 million lines of code in it. So what do we do? Well, so most of the time what we do is we build a perimeter, we patch every week or every 2 weeks, and then we pray. And it's not working very well. There's a lot of people have lost their identity, have lost their credit cards, or have been ransoms. It's not a very good approach. And here's a chart that ends with the E-Class Mercedes, which is what I mentioned, 100 million lines of code. Windows 7 is about 40 million lines of code. Even MS Office is about almost 30 million. But meanwhile, we've studied what they tend to use in terms of malware, and it's lots of little programs. Even Stuxnet, which was very sophisticated, was made up of a lot of small pieces that are averaging about 125 lines of code. So this is a number that, I got this 2 days ago. It may have gone up a little bit since then. It's the total number of unique vulnerabilities that the MITRE and NIST track. So across all of the world's software that has where vulnerabilities have been found, this is the number of unique different ones, which is still a really large number for someone to start going through that list and trying to use to exploit against the billions and billions of lines of code out there. So this is, of course, obvious, but it's still worth saying out loud in that when you're not talking about authentication attacks or software or social engineering attacks, and maybe the rare, really sophisticated side channel attack that can watch the electromagnetic emanations from your devices, but all the rest of these are because there's a bug in the software, and they're able to use that as a vector of attack to get in. People like Steve McConnell, who've studied this a lot, and wrote several books about writing secure code and just software engineering practices in general, has found that across all types of applications that have been deployed, so we don't mean in the lab, that have been deployed, no matter what the programming language, consistently are about between 15 and 50 bugs per 1,000 lines of code. And about 10% of those are potentially can be turned into attacks, cyber vulnerabilities. So the Mercedes has, by this, give them credit for the low number, 1.5 million bugs and about 150,000 vulnerabilities. And we know of some of the vulnerabilities. There's an application you can research and get that on your laptop that has a Bluetooth and Wi-Fi driving along the road, can get into the wireless air pressure sensor, the architecture of those cars with one single bus that communicates all information to anyone on the bus that's interested in it, can actually construct a malicious packet to the engine control unit and floor the accelerator. And as the chart showed, the battle is asymmetric. We're building bigger and bigger systems. And even when we start patching, it turns out now that one of the most frequent ways in which an enterprise is attacked is through their intrusion detection systems, because they're about 10 million lines of code and have bugs in it, and almost always need to have privileged access to the rest of the system. So why haven't we, if we've got all these billions of transistors, why haven't we as an industry, why has the computer industry really attacked this problem with a vengeance? And there are, I think, a number of reasons for it. One is that when you have an installed base of millions and millions of applications on billions of devices, you're not going to make radical changes. You're going to work in an incremental fashion, and so they're not going to break things. So why is everything so vulnerable? Well, we have a lot of software that's actually not that well understood. We were asked to take a look at a major weapon system for the Navy, and we went in there with what we thought was a reasonable question, which is, well, what do you think your cyber vulnerabilities are? And they said, you don't understand, that's not a reasonable question. We don't even understand how it works. Can you help us understand how it works? And I probed a little further. Why is that? Well, it was originally written in Jovial. How many of you have written in Jovial? Okay. So then when man's last great programming language called Ada came out, they translated Jovial to Ada. And then about 2 weeks later, when everyone realized Ada wasn't that, they translated it again to C, which is where it is now. But the people that wrote the original Jovial code, it's not just that they don't work for the contractors anymore, they actually aren't alive anymore. So they have this problem. Increasingly, we have been, as computer scientists, we have been making great strides in our ability to do formal verification of systems, but not systems that are really complicated. That's still way beyond the reach of doing the formal methods, proving some property that you want to validate in your software, hardware as well. So we still tend to write pretty monolithic software, so and the operating systems are extremely guilty of this. So if you can compromise, get access as root or super user, you pretty much can take over the entire machine. Whereas we've known for a long time, if you wrote critical services as a set of independent entities that only had what's called least privilege access to what they need, then you compartmentalize the system, and all hope is not lost if somebody compromises one of those services. We also, if you were to try to come up with abstractions for most of the hardware we have, it's very difficult to do so, and people aren't willing to pay the performance costs to create those kinds of effective isolations in the hardware either. And then this is the key time when the computer industry was just getting started, and really all that mattered was smaller, cheaper, faster, and climbing up that Moore's Law curve quickly. So this is what that architecture looks like, and those of us that have been working in this area for a long time call that single undifferentiated memory raw seething bits, because the processor has absolutely no idea what anything is. It's just told, go execute at this address. And it says, okay, that must be an instruction. It treats it as an instruction and starts executing. So if somebody finds a buffer overflow vulnerability and can use that to download a bunch of their code, instructions for this processor that they're targeting, there's a really good chance they're going to be able to also figure out a way to get the processor by changing the return address from the function that's on the stack to the beginning of their code. And now the processor has no ability to help you stop that, because it doesn't know what's a pointer, what's a buffer, what's an instruction, what's just data for a SQL query. And so this is part of the problem. So what we set out to do, this was initially a project that DARPA created as a result, a reaction to Stuxnet. So yes, it's true that Stuxnet was a cooperative effort between one really little company on the Mediterranean and one, did I say company? I meant country. And a really big country in North America. And it still scared the people at the Pentagon, because they realized that we'd let the cat out of the bag, that we were going to teach people how to do attacks as sophisticated as Stuxnet. And following Stuxnet, of course, was Dooku and Flame and Red October, and those were not all perpetrated by the same people as Stuxnet, yet they have the similar kinds of look and feel to them. So what this program that DARPA created in 2010, which was called CRASH, they ended up spending $100 million on this research program, and CRASH stands for Clean Slate Redesign of Adaptive Secure Hosts. So start over and don't be tied to the architectures of the past. And is it possible to make something that would be immune to the type of attack that Stuxnet represents? So take advantage of inexpensive hardware. Follow well-known security principles like the ones I just mentioned, least privilege, compartmentalization, and use a lot of formal verification because you don't want to have to test this kind of thing and come up with elaborate manual tests to try to, because you're never going to get coverage. You're going to miss too much. And so the idea was, okay, we're going to use these cheap transistors, and we're going to essentially, the key here is, can the processor and the application/programmer cooperate such that things that you meant to have it do and meant not to have it do are, in fact, the processor is informed about that and can avoid these kinds of issues. So this alone is not a new idea. Tagged memory architectures are not a new idea. The Lisp machine is a tagged memory architecture, but mostly for other reasons, like garbage collection. There was a Burroughs machine that was a tagged memory architecture, but no one has really kind of taken the tagged memory architecture to its sort of natural, to the extension where it can really collaborate with the processor in terms of security. So an example is that, so you have a word in memory and associated with it is another word. So yeah, it looks like we've just doubled the use of the memory, but transistors are cheap, and besides, we can optimize that a little bit. So the metadata has things in it like I'm an instruction, and there's also a rule that says anything that comes in over the network is always data, and you cannot change those things. The compiler is a trusted piece of software running on this machine. It can specify what's an instruction, and that's it. Also, something is established as a pointer. That is the first address of a buffer, and what the metadata has is this is the beginning of a buffer, and the buffer is this long. So with this, we can start to control provenance, who owns certain things, and fine-grained access control. So with this, we can actually implement, on the military side, multi-level security. This is top secret, this is public. In the rest of the world, this is personally identifiable information, and it will never be anything lower than that. We can actually have other types specified with this, instructions. And also, we can prevent what's now one of the more dangerous types of attacks that the sophisticated folks are using is called return-oriented programming attacks. And we can also, this can prevent that from happening. So we created an entity the hardware is modified first with the metadata, and then with something that's called a PUMP, which is a programmable unit for metadata processing. So a standard, very simple kind of normal processor execution flow is on the left, and there's the program counter, and there's where instructions are stored so that it can fetch the next instruction, and there's where the registers are, you know, the registers that are storing index variables and things like that. And then you've got the ALU, which is doing the add, subtract, multiply, divide, jump, and you've got memory, and you've got results. And so the little green on the left side of each of those things, including the PC, including all the registers in the memory, is the metadata tag. And in parallel with the ALU is something that is looking at the tags and making a decision as to, is this operation that the ALU is doing the same time as me valid? Should it be allowed? So the idea number 2 is that what the metadata in general point is a pointer to memory, so that we can have arbitrary security policies, not just I'm an instruction and I'm data. So you know, here's a list of the kinds of things, kinds of policies that we can create that the pump mechanism can enforce. So as the ALU is processing, the pump gets the metadata from the tags of the appropriate operands and the PC, and it, if necessary, it goes off and gets the policy that is pointed to in memory. Now, in practice, it rarely does that because we create a pretty large cache that rarely misses, so that as the pump is looking to see is this a valid operation, it's able to get the answer by just looking at the cache. And I'll show you the results of this in a minute. The kinds of things you can do in these micro policies, which is what we call them, is large. In fact, these are security policies, but we can also, we have safety policies, are sort of the first cousin of security policies. So for example, suppose that I have that my processor is in an insulin pump, and I would like to create a safety property that I would add to this list that says, even if the programmer made a mistake and we get to this point in the program where we're about to tell the pump to inject some insulin, if that means we will have injected more than X milligrams in the last 24 hours, alert the user, alert everybody you can, and shut down, because it would be better to let the patient go into manual mode than to kill them. But that's, you know, and the same thing is true, by the way, with all of this autonomous this and autonomous that. We're going to have cars that drive and drones that deliver packages, and it's all going to be wonderful and autonomous, and there'll never be any bugs in that software. You might want some safety properties there. So this is it's a slightly simplified diagram, but what we did was we took a conventional processor and we got into the guts of it and modified the instruction processing pipeline and added the stage down at the end, near the end, called the pump. So it's not a very big change to an existing processor. The processor that we're doing this to right now, we did an initial test in simulation a year ago on the DEC Alpha processor. So when we first started with the whole big crash program I mentioned, we took the clean slate part of that really seriously. And we invented a new instruction set architecture and a new operating system and everything, just so that we could prove that this was possible. But that was research. Now, what we're doing now is we'd like to bring this out as a real processor that could be used in embedded systems. And why do I qualify and say embedded systems? Because embedded systems tend to have a fairly small software stack compared to this ginormous software stack that you have to deal with on servers, not to mention the huge operating systems. So to get started and to start attacking the problem at some pretty meaningful places, we're focused on embedded systems. So with that processor on the alpha, we were able to enforce 4 things simultaneously. That was all we really wanted to prove. Memory safety, which means buffer overflow is actually impossible to have happen. Control flow integrity, which prevents changing where the processor is going to jump to, or where a return address actually returns to. Taint tracking, which is am I about to release top secret information down a channel that's public? And type separation, which it basically is helping what we try to have our programming languages do, but sometimes they don't really do. We ended up having a performance penalty of about 10%, and a modest energy overhead, and at least for this experiment, it was 2 times the area that we used. We used exactly twice as much memory. But we didn't do any optimizations. So the other cool thing about this is that we're not etching silicon specifically for any policy. These are all policies that it's like microcoding. And so if we find that there's a new attack that is able to successfully get into this machine, we can deploy new policies. So there's the basic diagram of how this works. So like we said, there's metadata bits attached to the word. The pump's going to resolve them. We set it up so that the programmer doesn't have to worry about the number of bits that is in the metadata, because it's basically a pointer to an arbitrary policy that they write, and the logic that's being performed by the pump once the rules are written is a black box to them. They don't need to worry about that. So they can just think of the metadata as a pointer. So here's how it basically, this is the abstract function of the pump. So the opcode, which might be add long, or jump. And then the following 5 things are the tags, not the PC itself, but the tag on the PC, the tag on the instruction, on the opcode 1, opcode 2, and if there's any memory reference. And then all that comes out on the backside is, first of all, is this instruction going to be allowed to happen? What's the new tag on the PC? And if there is one, what's the tag on the resulting operand? So I will show a couple of examples of this. So here's how we do this for a buffer overflow. What we do is we say when a pointer is being created, like by the compiler when it's creating the stack, or by malloc when you call malloc for storage on the heap. There's a unique color that's assigned to that pointer, and then to every one of the metadata bits for those words in memory. So now you've got this region of memory that's, so to speak, is yellow. And this is the policy then on a load instruction, which is that it says, and R1 is where the pointer to the buffer is being referenced from. And what it's saying is this is allowed because that first location in the result is whether it's allowed or not. And the answer is yes, if the memory location that you're referencing is the same color as the pointer. And if you go one word past the end of the yellow buffer and you're in the purple, this will cause a segmentation fault. And then your fault handling will have to deal with it, but it will not allow that write to occur. So if you take out all social engineering, password guessing attacks, which we would just like to see people do better at those. 70% of the remaining attacks are memory misuse, which would be caught by that previous. Now remember, if you've got a lot of code that you've written, you've got a lot of buffers that you've used. You've gone through carefully and you've tried to make sure that you've done the right thing with the buffers. But it's like a house that has 100 windows and you lock 99 of them. So you'll catch the 99, and the processor, even when you've done a really good job, you might miss one, the processor won't even let that last one go through. And that's what we mean by the code and working with the processor to enforce this. Here's another one, which basically says at the time that a call occurs, get the list of possible targets that it is legal to jump to when the call is returning. And so then, which the compiler knows, of course. So the PC is constantly being tagged with where am I right now before I execute the next instruction. And it's got a list of the legal caller tags. So now when the instruction is not a call instruction, it's able to say, am I jumping to a place that's legal for the function that I'm currently in? And that stops a return-oriented programming attack and, in general, control flow integrity. And I'm just going to show one more. Taint tracking is also used to declare a rule that says no data that is considered confidential or personally identifiable can ever leave the machine unless it's encrypted. So you taint the PC such that rule is activated, and then at the moment that it's about to be written to a register in a device driver, it's checked and it says, I'm about to write something that's not encrypted, that's a credit card number. And it would basically kick that back, and this allows you to also say that everything coming in that's considered personally identifiable or confidential is also encrypted. So it's not that useful if there's only one security policy at a time, and so the tag can point to essentially a list of as many as you want. And I normally don't put up things and say, oh, this is an eye chart. I wanted you to just look along the bottom row. So the labels are things like type information, memory safety, control flow, taint tracking, and in all of these cases, the runtime overhead was between 8 and 13%. There's one outlier, which is because we really tried to do taint tracking at too fine a grained level, and it was per function, and we had, for the spec benchmark that we used, it ended up just exploding, and so we'd have to back off from that level of granularity. But that's we were very pleased with this runtime, even though we were tracking 4 policies simultaneously all the way along. So I mentioned formal methods. So each individual policy is simple enough that we're able to build proofs in the Coq programming language, or the proof language. If you're not familiar with it, the French are the leaders in formal methods, and they created this language, Coq, and it means rooster, and it's the symbol of France. So it is by far the best. Well, they all say it's the best proof language that the formal methods community is using. So they were able to apply this to information flow control, which is the data equivalent of control flow. That is protecting against exfiltration of data as my secret data leaked out. Then they were able to verify that the implementation of it was correct down to the hardware level. We're applying some random testing as well to verify all this. And you know, we're going to continue really hard on the formal methods on these policies. We've done a little bit of optimization so far, and we've reduced the overhead. Remember I said at the beginning, the area was double, and we've gotten that down to only be essentially 10% higher. There's a couple of outliers. The bottom names are from the spec benchmark that we were using. And in general, we got, you know, really dramatic improvements. And in a few cases, that's runtime on the top, and that's energy over here, and area is way down from 200%. So energy overhead, as I quoted earlier, 60%. Runtime overhead, actually even as low as 7%. We tend to quote 10% just to be safe. So, so here's where Draper came in. We started in this project at Draper in July. We took, basically, it was my team that was doing this under DARPA, and now we've moved the team to Draper. Draper is very committed to investing in this themselves and then providing this to both government and commercial entities that have embedded systems. And so the processor that we decided to go with is the RISC-V. It's open source. Now it's been adopted by Google and the Sun division of Oracle, which it pains me to say. But they are looking for a replacement for the Spark, and it looks like it's going to be the RISC-V. We hear rumors that a lot of other people are very excited about this. It's been in development for almost 15 years, so it's not new, and it's driven by the guy at Berkeley who is essentially the father of the whole RISC concept. So because RISC-V exists with a Linux that works for it and a great tool chain, it means we can get something up and running fast. And in fact, we started in July, and we'll have a fully working system in February. We're doing a full suite of the policies, and we're developing actually a language for specifying policies and checking them. We will modify the compiler. The compiler has to be modified because it has to generate some of these tags. We'll have to run through all of Linux. Even though Linux works on the RISC-V, Linux has places in it where it actually writes past the end of a buffer. It gets away with it because nobody else needed that word or words past the end of the buffer, but as soon as you try to run that on this processor, which, by the way, as I had it on the previous slide, we call Dover, which is short for do-over. And these are the other things that we have to build in this time frame. And we're going to try to go further than just making sure Linux runs, but actually start separating it out into its components. And so the other thing that we're trying to do is to create a community. We're calling it a HIVE, a community of entities, companies, government agencies, universities that want to work together to make systems that are inherently secure. We're hoping to have them influence what the future direction of this should be, share with each other what they're learning, maybe build this chip into their embedded systems, and get a lot of interaction with my team as well. We have some very large companies and universities involved so far. It's looking to be a pretty nice community of people really anxious to change the game on the attackers. So I just want to summarize. We know our processes are really insecure, and the architecture that we've been using for a long time is actually complicit in that. But now, with so many transistors, we can actually take advantage of them and use some of them for security. And when people worry about, can I really afford 10% performance overhead, you have to put that into context of, so what did that cost target? And so we've got, we're one of a long line of people that have figured out how to use metadata tags on hardware. We just think we're going further than anyone else has with it. And that includes safety. And the way we're developing this, it's with a set of tools for it. It's going to be like developing software, micro-coded software specifically for security, but with the same performance as if it were in hardware. So, can I answer any questions? Yeah.
So in terms of the metadata, if somebody tries to pull that capacity for the processor to get it to do bad things, is that, I'm still kind of fuzzing exactly.
So,
if somebody can fuzz the metadata tags, they can still get whatever supposed to happen.
So the metadata is actually not addressable by any software or any hardware except the pump itself. So it's not possible to come in from the outside and address it. I mean, and we know that kind of mechanism works. We know page tables work. We know those kinds of mechanisms work. So that's completely opaque. You won't see you won't even see those addresses. You will only see the addresses for the payload words, like in a normal machine. Now, I'm not going to stand up here and say nothing bad will ever happen. We're trying to take a giant leap, and then we think we have a mechanism where if somebody figures out something that we didn't think of, that we can adapt to it. Yeah.
It sounds like if I were a programmer, I'm not, I suck at programming, but if I were on a system like this, I have some measure of control of types of ways that I want to tag data. For example, saying this is PII and I want to have certain properties. But so if I wanted to write specifically the architecture, I could, but a lot of it would just be automated and compilable so that, for example, the separation between instructions and data, I don't have to write a program differently at all.
That's absolutely right. So existing applications on these embedded devices will port through a simple recompile and run a series of tests to make sure that they don't do any of these things that the processor wouldn't allow. Then, if you want to go further, and I'm just restating what you said, but it's exactly right. If you wanted to go further and declare something as PII, this is a social security number, we do have to add a couple of extensions to C to allow you to specify that, and for that to get pushed all the way down into the metadata tag so that the processor knows that.
If I were able to get a piece of malware on something that could modify a binary that is sitting on a disk, would that allow me to then bypass some of these mechanisms by changing what the compiler had written?
So we're in a machine like this, if somebody gets physical access to it, then pretty much all hope is lost. And so but you say, well, wait, in an embedded world, physical access prevention of physical access can't be guaranteed. So one of the great technologies that Draper is the lead in the world at is anti-tamper technology. We have to be good at it because it has to be on all of the military stuff that we create, and we now provide that to other companies. So when when a fighter jet is sold to even an ally, Egypt, everything in it has anti-tamper on it. So we will make sure that our stuff has that on it. So yeah, physical access is really important. We're even worried about some of these side channel attacks, and we've got one of the people in this so-called HIVE who's looking at what are the things you could do ahead of time to prevent these side channels, side channel attacks. Side channel attack, for example, can, from 2 feet away, you can actually see the power fluctuations in a standard processor enough so that you can actually spot when it's running AES encryption. If you run it for about 15 million times, you can actually extract the key. So we want to make sure there's a countermeasure to that as well. Yeah, so they're in, the micro policies are secured by being put into an encrypted store, which we have to manage the key for, and you do have to have physical access. There is no updating of the micro policies over the air because that would just be too dangerous. So if you're going to download a new micro policy, it's got to be code signed, and then it's stored. Yeah. So yeah, we do have a TPM on board the chip so that we can manage the key encryption and everything. It's not easily accessible, but it has to be accessible through a very one path only. It's similar to the fingerprint reader on the iPhone. They did a very good job on it. There's almost no code at all between the hardware detection of the fingerprint and it getting into the application that's asked, is this who they say they are? So a similar kind of short path. Yeah.
So do you see this work? I mean, so right now you said you're looking at just using this on embedded systems
Right.
and such. But
Right.
So rolling it forward as so things like GAP and ASLR, do you see it's working in parallel with that, with those things, sort of layered security, or
So that, that's exactly the kind of thing that we would like to have people working on with us in this little hive. And just looking a few years out, because so before I did any of this defense, or lab work, I was a serial entrepreneur, started several security companies and whatnot. So I'm treating this like a startup. You don't try to boil the ocean on day one, right? So you pick a niche and you try to get really good at it. And I think it'll take us about 3 years we'll have 6 significant customers by then, I project. And then I think we'll be ready for what's the next step. Now, Draper never wants to become a chip company. It's not ever going to do that. But Draper could do what ARM does. ARM licenses, ARM makes nothing. And they make $1.25 billion a year just writing contracts and collecting checks for royalties. So we could license it, we could sell it to a bigger chip company, and a lot of the security things that you're concerned about being applied here, we could start working on those early or as it starts to take off. We joined the RISC-V Foundation, so we're the 3rd member. very pleased, Google's first, Oracle second, Draper third, sort of a but the reason I mention that is that the whole foundation is very interested in standards applied to the RISC-V, security in particular, and sort of this ecosystem that could grow up around an open source instruction set architecture. And I should mention that there's a little bit of secret sauce that we'll keep back, but we're going to put everything else we do back into open source. Yeah. Yeah, so I can give my card to anybody that wants it, and I can send you those. Any more time? Do I have time? Okay, well, we started early, so we'll finish early. You have a question? So I don't know the answer to where AMD is, but Intel is coming out with another set of small additional set of instructions called MMX, I think, or is it MPX? And they are designed to, it's going to take a while because they have to be rolled into the operating system, the programming languages, et cetera. But the idea of them is just to stop the buffer overflow attacks. So I think you'll see those in the next, they're probably invisibly in the current chips, but you can't access them because they're not fully debugged yet. So you'll probably see them in the next generation of Intel chips, but you probably won't yet see support in all the rest of the tools. So it'll probably take another, I would say, 3 to 5 years before those come out. And that's, one piece. So they're doing an incremental approach. The problem I have is that the Intel chip, nothing's been thrown away since the 8080 in 1986, and so it's extremely complex. You can't prove anything about it. Whereas when you go back to a RISC processor, which is clean, especially this one because it's relatively new compared to ARM's an older RISC design that's had a lot added to it. MIPS, of course, has been around a long time. So it's kind of a nice place to start all this. Yeah.
You mentioned you have TPM in there, TPM capability. Does that apply, and this is obviously not applicable for a general purpose CPU, but for embedded systems, if you then force the CPU to only, for example, run binaries that were generated and signed by your compiler, does that make sense to you?
You could do that.
Have it enforced by the CPU.
And have it enforced by the CPU, yeah. Is there a question over here?
So you had mentioned how much reasonable breaches cost a target. But if you go out and look at Google Finance today, Target's enjoying a stock price somewhere near a 5-year high right now. So my question is, are there enough economic drivers in place to drive the adoption of a chip that might cost a little bit more, when investors don't penalize companies for insecurity?
No, it's a very good question. And I fear that as a country, we tend to wait until there's a huge disaster to react, which is another really good reason for us to focus on the embedded systems market. We have a limited amount of bandwidth, so I'm going to be very selective, and the first two whose hair is most on fire about security are going to get our attention, as the first two customers. One of those seems to be this glucose monitor, because they want to start surgically implanting glucose monitors. Pricking the skin, not good, and the fact that if you only have the patient monitor their blood glucose level every so often, it's not continuously monitoring, and so, you know, whereas in those of us that you know, generate insulin the old-fashioned way, you know, we follow the curve of you know, the eating and the sugars and et cetera, and it's unhealthy for them that they don't, so they want to embed these things. So their hair is on fire because they know that one highly publicized incident on their device, and no surgeon is going to be allowed by their patients to open them up and put this inside. It's not that there's a terrorist attack, it's that, you know, somebody attacks it because they can, and then it gets publicized. Another one that we're talking to, and I can't mention any of the military ones, but a little company makes this device that monitors the temperature of something that's critical, like a big, huge tank that could go boom, or things that are refrigerators or freezers that have FDA-regulated things in them. And they then send that information back over a cell phone to, it's encrypted as it goes, to wherever's being monitored. But the devices themselves are running the standard processors that are vulnerable. And this is a company that, you know, they've got 100,000 of these devices installed, but they're still not a big company, and one incident could destroy them. So Target survived, but you know, someone else might not. Great, thank you very much.